The modern artificial intelligence ecosystem has completely fragmented the outdated concept of the universal monolithic database system into specialized components. Building a production-grade AI application requires the simultaneous management of unstructured raw media, high-dimensional mathematical representations, continuous GPU training pipelines, and structured analytical metadata. Attempting to force all of these disparate data formats into a single storage system creates massive computational bottlenecks. The system spends more time translating data shapes than processing them. To resolve this friction, modern AI architecture relies on a composite stack of 5 highly specialized database systems. This ecosystem splits strictly along 2 axes: the primary geometric format of the data being stored and the primary mathematical logic required to query it. We can divide these 5 categories into 2 distinct operational families: the mathematical array engines and the tabular context engines. Architecting infrastructure for AI requires mapping the specific geometric shape of your data to the correct computational engine. We begin with the mathematical array engines. These are the systems built specifically to ingest, store, and manipulate the raw numerical formats generated by AI models. Vector databases process one-dimensional vector embeddings, flat numerical arrays capturing the semantic meaning of unstructured inputs, like text or photographs. Because the format is spatial, the query logic is geometric, using metrics like cosine similarity to locate nearest neighbors. This specific combination of 1D geometry and distance logic drives semantic search engines and provides the context retrieval mechanism for large language models through retrieval-augmented generation. While 1D vectors handle semantic lookups, the actual deep learning models require a more complex geometric structure. Tensor and array databases manage n-dimensional dense or sparse arrays. The geometry here scales outward to 2D, 3D, 4D, and higher. In an AI pipeline, these multidimensional tensors represent heavy assets: video sequences, satellite imagery, attention matrices, and neural network weights. Querying this n-dimensional geometry requires high-speed, multi-axis slicing and linear algebra transforms across millions of data points simultaneously. This approach solves a critical hardware bottleneck. During model training, GPUs compute data much faster than standard storage disks can read it, leading to starved processors and wasted compute cycles. Tensor databases bypass this by streaming raw, multidimensional data chunks directly into PyTorch or TensorFlow data loaders without triggering disk read delays. If you need to mathematically measure semantic proximity, you use 1D vectors. If you need to feed multidimensional data blocks into a GPU at high speeds, you use tensors. AI models operate on mathematics, but autonomous AI agents must interact with the real world. That requires tabular context engines, which enforce structured business logic. Analytical engines and cloud warehouses sit at the center of this tabular ecosystem, managing metadata catalogs and structured domain data. Their primary data format consists of structured tables and open file formats, highly optimized for column-based reading, like Apache Parquet. The query logic here is entirely focused on executing high-speed SQL aggregations, scanning billions of rows to calculate averages, sums, and distinct groupings. Recently, modern analytical platforms have integrated the Model Context Protocol, or MCP. MCP servers bridge the gap between AI and the warehouse. An AI agent issues a natural language query. The protocol translates it, executes the SQL scan, and returns the aggregated context directly to the agent. Alongside these analytical warehouses operate traditional relational SQL databases, such as PostgreSQL and MySQL. Analytical engines scan broadly, but relational databases are optimized for exact operational lookups. They execute precise where queries to find a single specific row instantly. In an AI architecture, these relational databases manage the strict transactional state. They handle user accounts, system logging, and serve as highly durable metadata backends for the catalogs. Analytical engines provide the massive contextual intelligence required by AI agents, while relational databases maintain the exact operational memory of the application itself. All 4 of these specialized databases share a single constraint. They require massive amounts of persistent raw storage that remains economically viable at scale. This introduces the 5th type of system, which sits at the very bottom of the data stack: open lakehouse catalogs and object stores. The architecture here is a hybrid. It pairs extremely low-cost cloud object storage, like AWS S3 or Cloudflare R2, with sophisticated database-backed metadata catalogs. This structure allows engineers to store petabytes of data in open columnar formats, while the catalog layer enforces schema-wide ACID transactions and guarantees sub-10 millisecond indexing. The Lakehouse acts as the unified long-term memory for the entire stack. It houses unstructured raw assets, sprawling model training sets, and tiered layers of analytical data. By providing cheap, durable persistence, open lakehouses ensure that the high-speed math and analytical queries happening in the upper tiers are physically and financially possible. This comparison matrix charts how a mature AI pipeline routes data based entirely on its geometry and the required logic. If the pipeline is processing 1D embeddings and requires k-nearest neighbor similarity, the system routes it to a vector database. If the workflow is feeding dense, multi-dimensional arrays to a GPU for deep learning training, it routes to a tensor database. If an AI agent needs tabular aggregations to establish domain context, it queries an analytical engine via the Model Context Protocol. If the system requires persistent, massive storage for its raw, unstructured assets, it defaults to the Open Lakehouse. And if the application needs exact keyword matching and highly durable state management, it relies on a traditional relational database. Executing semantic search in a SQL database or attempting exact keyword lookups in a vector space guarantees friction. The geometry dictates the engine. Managing AI infrastructure means abandoning the search for a single universal database. The modern stack is an orchestrated architecture defined by geometry and logic.